A burner management system is used on heated vessels in the oil and gas industry where precise temperature control is needed. In this video, we'll discuss a burner management system and cover the following topics. A burner management system, or BMS, is a combination of products that control and monitor the temperature in a heated vessel, control safety systems used to ensure safe startup and shutdown of process burners, and operate fuel trains. You'll find a BMS anywhere that heat is being controlled within a vessel, such as a heater treater, line heaters, and some horizontal separators. The easiest way to identify a heated vessel is to look for the flame arrestor and stack. These are easily recognized pieces of equipment that signify when a vessel is heated and a BMS could be in use. A flame arrestor allows air to pass through but stops the propagation of a flame. The stack exhausts the hot gases out of the fire tube and draws in fresh air for the burner. Without a burner management system, if a pilot flame is extinguished, the burner gas will continue to flow even without the proper temperature control. This creates a dangerous situation and increases the chance of fire and accidents from the burner gas venting. There are two kinds of heated vessels producers use. The term direct fired means that the heating element is providing heat directly to the product being processed. Examples of these types of units are glycol reboilers and heater treaters. The term indirect fired means the heating element gives energy to a fluid media, often called a water bath, that then heats the well stream. Examples of these types of units are line heaters and gas production units. A manual BMS has controls that must be manually adjusted or started. These systems can use a pilot light to ignite the main burner and are referred to as a freestanding pilot burner. The pilot light needs to be manually ignited in the startup process. The T12 temperature controller is used to operate a pneumatic low-pressure control valve when the temperature needs to be adjusted. While manual BMSs have historically been the standard, they can put the operator in a potentially dangerous situation during the startup process. Using a standard line heater as an example, we'll start by looking at the supply gas regulator. This regulator supplies gas to all the pneumatic controls in the BMS. It initially leads to the pilot guard, which then feeds the level switch, followed by a high temperature shutdown and thermostat. The pilot guard is directly in the pilot flame, monitoring the freestanding pilot burner. If the flame goes out for any reason, it shuts the supply gas off to the rest of the system. This prevents natural gas from going into the burner without a pilot flame and being emitted into the atmosphere. It makes sure that the pilot light is lit and that the gas is being consumed. For safety measures, when there is a BMS, there's also a liquid level switch used as a low-level shutdown. When the heat transfer media drops below a certain level, it will expose the fire tube, in turn creating hot spots and compromising the fire tube. If the level switch is tripped, it cuts off all supply gas to the BMS, removing all fire until the liquid level is increased above that point. The high temperature shutdown monitors the temperature as a safety backup in case the T12 fails and the temperature rises. Once the fluid gets to a predetermined temperature, the high temperature shutdown removes all supply gas to the burner by closing a valve upstream of the primary burner, so it can no longer heat the vessel. The high temperature shutdown is made up of a T12 and a manual reset pilot. Once the set point is reached, the high temp shutdown must be manually reset to supply the burner with fuel. This ensures that an operator must go to the location to inspect the equipment and fix the issue that caused the overheating before they reset the high temp shutdown. The pneumatic thermostat is installed where it will be immersed in the liquid to be heated. The thermostat monitors the liquid temperature and expands and contracts with the temperature change of that fluid. This positions the pilot plug to either vent or output a pneumatic signal to control how much fuel the burner is receiving via a pneumatic low-pressure control valve. For a more technical explanation of what is happening inside the thermostat, watch our video about the operation of the T12 thermostat. This pneumatic signal from the T12 is sent to the burner valve. The burner valve opens and lets the appropriate amount of gas through to the burner to increase the temperature. The valves used in this application are double acting, meaning that there are two forces acting on the valve. The spring moves the valve stem into the fail position, and the diaphragm supply pressure coming from the T12 will move it in the opposite direction. These systems are not exactly the same, but they will use the same principles that the supply gas is always fed through the safety systems before it gets to the burner valve, ensuring that if any safety systems are tripped, the burner valve is shut down completely. While a manual BMS uses supply gas to control its pneumatic components, an automated BMS requires low-voltage electrical power to control its electronic components. An automated BMS can sense when the burner needs to be extinguished or relit and can complete this task automatically. These systems communicate with low-pressure control valves such as the Kimray ELO. These automated valves release the appropriate amount of gas into the burner in order to maintain the desired temperature. Automated BMSs will have an electronic ignition system that keeps the operator out of harm's way. These systems eliminate the possibility of a constant pilot light being blown out and minimize fuel consumption and atmospheric emissions. Electronic ignition systems are also much safer for the operator in the event of a backflash or equipment fire. Using a heater treater as an example, we'll start by looking at the resistance temperature detector, or RTD. An RTD senses the temperature of the production fluid and sends the appropriate electronic signal to the burner valve to adjust the amount of fuel it's providing to the burner to maintain a temperature set point. RTDs have high accuracy and repeatability, which is key to any BMS. The ELO control valve is a dynamic, low-power, low-pressure controller designed to control the flow in applications less than 45 psi and can be used with an automated BMS. In this scenario, the ELO will receive an electronic signal from the RTD and move to the appropriate position to control the amount of fuel it's providing to the burner. In an automated BMS, an electric level switch will be used as a low-level shutdown. The switch stops the fuel from traveling to the burner in case of the liquid level being too low, exposing the fire tube.